Hi there. Welcome to Tech Talk Weekly. I'm Bob from Creation Station. This is our weekly show where we give you 2 to 3 cool news stories, tell you a fun library fact, and get you on your way in 15-20 minutes. That's not happening today, guys. We are going to show off a really fun thing today because I have Miss Patricia Moore from NASA here. Patricia, how are you doing today?
I'm doing great. Thanks for having me, Bob.
Are you there, Miss Patricia?
I am. Can you not hear me?
I think we're having a problem with you hearing.
I can hear you. I can hear you.
There we go. Now we can.
Okay, great. Yeah.
Okay.
So I was telling you and everyone that's listening, thanks for having me.
Beautiful.
Everything's good.
So, Miss Patricia, here's from NASA. Tell us, who are we going to be able to talk with today?
Sure. So I work at the Johnson Space Center and I'm part of the Artemis communication team. And we're doing a series of events over the summer to share what's going on with our Artemis missions. And today's special guest is from the Kennedy Space Center Exploration Ground Systems team. And his name is Eric Weaver. And he is the engineering deputy director for the Jacobs team, who is the prime contractor, the prime company that's working to get all of our rockets and systems ready to go to the moon. So, Eric, thanks for joining us today.
Yeah, thanks for having me. Appreciate it.
All right. Do you want to just jump right into the presentation, Bob, and get going? There we go. All right. Well, I will go ahead and progress slides. So just let me know when you're ready, Eric.
Yeah, we'll do. So yeah, thanks again for the introduction and thanks for having me today. I really appreciate it. And I'm glad that everybody's here to learn about the spaceships that I get to work on every day. So I guess we'll just start with the next slide. So like Patricia said, my name is Eric Weaver. I am the Deputy Director of Engineering for the Jacobs team on Exploration Ground Systems at Kennedy Space Center. I grew up in Western Pennsylvania, just outside of Pittsburgh. Actually, ironically enough, I grew up in a town called Hollow, Pennsylvania. So should have been maybe should have been called Artemis, but in any case. I got a Bachelor of Science degree in Civil Engineering from Bucknell University. I got my Master's of Engineering degree from Lehigh University, both in Pennsylvania. I started on the shuttle program in 2009, worked on the shuttle program for a few years, and then after that, transitioned to the Artemis program here in 2013, and I've basically been here ever since. I'm a licensed professional engineer in the states of Florida, Pennsylvania, Ohio, and West Virginia. I'm a certified maintenance and reliability professional, as well as a certified project management professional. My hobbies include traveling, golfing, scuba diving, snow skiing, and cheering for the 3 Pittsburgh professional sports teams. And if you're a baseball fan, you might argue that one of them is not a really professional team, but nevertheless, they do compete in professional sports. And just fun fact too, I also applied to be an astronaut 3 times. One time I even got called back, which was pretty awesome because it's, I think probably, if not the hardest, maybe top 3, top 5 hardest jobs to get in the entire world. So it was cool to get called back at least one time. Next slide. So NASA has a lot of programs that they work on, and there's a lot of work to be done on those programs, and so much work so that they need private partners from private industry in order to help the government with these programs. And the one program that we're going to talk about today specifically is called the Artemis program, and the specific partner, NASA's partner that is partnering with them on the Artemis program is Jacobs, and that's kind of where I come in. So next slide. So in this video, we're going to see, how the boots on the ground are putting the boots on the moon. If you want to play the video.
module and service module have been fueled and are now being mated to the launch abort system prior to delivery to the vehicle assembly building for stacking atop the rocket. 50 years ago, NASA stunned the world by landing humans on the moon with the Apollo missions. Today, we are helping NASA to go back to the moon to build a sustainable human presence there. We are proud to be the boots on the ground that are putting boots on the moon.
All right. Hopefully the sound worked for most of you. I kind of got cut out there at the beginning, but hopefully you kind of got the gist of introducing our rocket and the Artemis program with that. So, with the Artemis program, like I said, putting boots on the ground, putting boots on the moon here at Kennedy Space Center, and stemming from Apollo. Artemis is in Greek mythology is the twin sister of Apollo, and the goddess of the moon. And our plan is to land the first woman and the next man on the moon by 2024. And then when we go to the moon, within the next decade or so, we're there to stay. So we're going to be building sustainable habitats there, and a lunar orbiting station that we're going to get into a little bit later. But when we do go to the moon this time, we're hoping to be there to stay, just kind of like the International Space Station, where we're built the International Space Station, and we are there to stay in low Earth orbit. So next slide. So like I said, NASA is working to establish a permanent human presence on the moon within the next decade or so. The moon will provide us an opportunity to test all of our new tools, our new instruments and equipment that can be used to go onto Mars from there, including the human habitats, the life support systems, technologies, and practices that could help us build self-sustaining outposts away from Earth. The moon is basically acting as our stepping stone to get much further into deep space, including Mars. Next slide. So with that, we got another video, and I want you guys to meet the Artemis team.
To go. With Artemis,
we are going to stay.
proving that humanity
can live on the moon,
Mars, and other worlds,
and share the wonders of the solar system with all.
Our story is one of people.
All those who make this journey possible.
From advocates across communities,
to companies across industries,
to countries around the world,
we achieve this collective endeavor.
Our efforts create impact for all.
Technologies that revolutionize industries.
And jobs that bring prosperity to people.
The discoveries from space
benefit the way we live on Earth today.
And those from the moon
will create a better future
for generations to come.
But to do that,
we must go.
Hi, I'm Chell Ingram.
My name is Raja Chari.
Kayla Barron.
Kate Rubens.
Hi, I'm Christina Cook.
NASA astronaut Joe Acaba.
Jessica Amir.
Woody Hoberg.
Ann McClain.
Stephanie Wilson.
My name is Johnny Kim.
Nicole Mann.
Victor Glover.
Jessica Watkins.
Hi, I'm Matthew Dominic.
Jasmine Mogbelli.
Frank Rubio.
Scott Tingle.
This is what we do.
This is what we will do.
Let's go.
We go to the moon to learn how to live on other planets.
For the benefit of all.
Awesome. So how are we getting there? Artemis is it's a multi-phase mission, including Artemis 1, Artemis 2, and Artemis 3, all in production right now. Artemis 1 to a very great extent, and even Artemis 4, actually. There's flight hardware being built and put together right now for Artemis 4 even. So we're well on our way with the Artemis missions, and especially for Artemis 1, as you're going to see. So right on this slide, you see the 6 key elements that are being worked. That includes exploration ground systems. That's basically all the structures on the ground that it takes to support launching and building the rocket and so on. The Space Launch System, which is the rocket itself. Orion, which is the capsule that sits on top of the Space Launch System. Gateway, the lunar landers, and even the Artemis generation spacesuits that you see on the right. So next slide. For the purposes of our presentation today and the work going on at the Kennedy Space Center, I'm going to concentrate on the first three, including the Space Launch System, the Orion spacecraft, and then the Exploration Ground Systems. Next slide. So starting with the Space Launch System, the Space Launch System, or the SLS, is the world's most powerful rocket, and it's comprised of four major components. The cargo hold, the exploration upper core stage, the core stage itself, and the solid rocket boosters. It's the only vehicle capable of sending humans to deep space, which is pretty much anything beyond low Earth orbit, where the International Space Station is orbiting. The SLS stands at 322 foot tall. It weighs 5.75 million pounds, and it has 8.8 million pounds of thrust. It has the capability of sending 154,000 pounds to low Earth orbit, which would be like the equivalent, as you see on the slide, of like 12 full-grown elephants. So SLS Block 1, which is for Artemis 1, is going to be the workhorse for the Artemis program. Next slide. NASA's Orion spacecraft will serve as the exploration vehicle that will carry the crew into space, provide emergency abort capability, and sustain the crew during space travel. Then afterwards, it'll provide a safe re-entry from deep space back to Earth. Orion will launch atop the SOS rocket and is designed to accommodate 99% of the human population. The spacecraft being 99% of the human population being, so anyone from like 4'10" all the way up to 6'5" would be able to ride in the space capsule and go into outer space. It can accommodate 4 astronauts, and compared to the capsules that you remember, maybe when you were younger, from Apollo or Gemini or Mercury, this thing is like a living room compared to those things. So much bigger, much more capability. Next slide. Jacobs is creating the tiles for the Orion thermal protection system. So as Orion enters the atmosphere from a mission from the moon, its heat shield must protect the vehicle and the crew from external temperatures of almost 5,000 degrees. So just for comparison's sake, the melting point for titanium is 3,000 degrees, and the surface of the sun is about 10,000 degrees Fahrenheit. So Orion will return to Earth from the moon at a speed of about 25,000 miles an hour. And if it were coming from a trip from Mars, it would be traveling at about 27,000 miles per hour. That's about 35 times faster than a speeding bullet. And like I said before, Kennedy Space Center is EGS, and and this is a big part of what we're working right now. So next slide. And with EGS, it's build, launch, and recovery. And we're going to go into these things a little bit more detail here in subsequent slides. But again, EGS, everything on the ground it takes to receive, process, fuel, transport, stack, launch, and then retrieve the spaceship once it comes back to Earth. Next slide. So build. To build the rocket, spaceflight hardware arrives at Kennedy Space Center from all over the country, and actually sometimes from all over the world. We have international partners in Canada, Japan, the European Union, you name it. And it's our team's job to accept the hardware, process the hardware, and then stack and build it in one of our processing facilities. So, for example, the one picture that you see on the right is a picture of our vehicle assembly building, or the VAB. The vehicle assembly building was built in 1965. It's one of the largest buildings in the world, and it stands at 525 foot tall. In fact, it's almost like a 500 foot cube, being about 500 by 500 by 500 foot tall. And that's where the rocket is built. It's basically a garage for rockets. Next slide. Probably one of the most exciting parts of our job is that we launch rockets. And we have to have special equipment and special software that helps us do that. That includes the crawler transporter that you see on the left, the mobile launcher, the launch control center, and Launchpad 39B, which we're all going to get into a little bit more detail in subsequent slides. Next slide. We also have a landing and recovery team that departs from Kennedy Space Center in Florida to recover the capsule from a U.S. Navy ship after it splashes down in the Pacific Ocean. And even before we go on the missions, we have practice recovery missions in order to test our capabilities to retrieve the capsule, and it also helps keep the team sharp that's working on the ship. Next slide. So Artemis 1 is the first in a broad series of exploration missions that will take humans to deep space and eventually to Mars. It's designed to be a flight test, basically, of our entire system because it's unmanned. For Artemis 1, SLS will carry the Orion spacecraft on a mission 275,000 miles away from Earth. And just to put that kind of in perspective, Mars, at its closest, is 36 million miles away from Earth. And that's give or take many, many millions of miles when it's at its furthest. Next slide. So in the next video, we're going to highlight some mission specifics for Artemis 1 and beyond.
Artemis 1 will lift off from Launch Pad 39B at NASA's Kennedy Space Center in Florida with 8.8 million pounds of thrust provided by the most powerful rocket in the world, our Space Launch System rocket, or SLS. The uncrewed flight will be the first integrated test of SLS, our new Orion spacecraft, and exploration ground systems at Kennedy. Artemis 1 will send Orion beyond the moon, 280,000 miles from Earth, farther than any human spacecraft has ever flown.
This is not NASA doing this. This is the United States of America doing this program, the Artemis program, and there are companies all across our country that have a part in it. So there is kind of this wave of excitement being generated just by saying we're going back to the moon.
After the upper stage of the rocket separates from Orion, the upper stage will deploy small satellites over several days to perform science experiments and technology demonstrations. Orion will make its multi-day outbound trip to the moon, propelled by a service module provided by the European Space Agency. Engineers will test Orion's systems on the way to the moon. Then, Orion will fly about 60 miles above the lunar surface, using the moon's gravity and engines on the service module to enter a lunar orbit. After about a month and a total distance of over 1 million miles, Orion will return home, faster and hotter than any spacecraft has before. A primary goal of Artemis 1, ensure Orion safely returns to Earth before we fly with humans. When we do, we'll build our capability for sustainable lunar exploration, preparing us for missions farther into the solar system.
Initially, what we'd like to do is start establishing a presence on the moon. So we're going to establish going back there on a regular basis, and then we'll end up setting up Gateway, and we would launch to the Gateway, and from Gateway, land on the surface of the moon.
We are there for, weeks, months on end. And there, we're going to be able to test out all the hardware and the habitats and the hatches and the suits and the rovers that'll allow us to prove out those technologies. The moon will lead the way to Mars, and we should be there within the next couple of decades.
All right, so building a rocket is basically a step-by-step process. I mean, it's a very complex step-by-step process, but nevertheless, at a high level, you can see that kind of the step-by-step process laid out on this slide. Some of the following slides will highlight some of the accomplishments that we've had so far in going through this process. So next slide. First was the solid rocket boosters. So they were the first to be assembled and stacked in the vehicle assembly building, and they are the largest ever built for human space flight. At 177 feet tall, each booster weighs 1.6 million pounds. The job of the boosters is basically to provide the thrust or the force necessary to get the rocket off the ground and on its way to space. Next slide. The core stage is pretty much that big orange thing in the middle. And it was lifted into place and very, very carefully between the solid rocket boosters using one of the 5 overhead cranes in the vehicle assembly building. At 212 feet tall, it's made up of liquid fuel, and that's the fuel that's used to feed the RS-25 engines, which are the 4 engines at the bottom of the rocket. Next slide. Next up was the LVSA, or the Launch Vehicle Stage Adapter. And it's that orange cone-looking thing that you see on the top of the middle picture. So you can think of this basically as a connection piece between the core stage and the next piece of flight hardware that we're going to cover, which is the ICPS, or the Interim Cryogenic Propulsion Stage. So it's basically a connection piece onto this, the ICPS, which was also integrated, stacked on top of the LVSA, and the ICPS, the Interim Cryogenic Propulsion Stage, again, will lie just below the Orion capsule at the top of NASA's space flight rocket. And it's a system that will help carry and propel the Orion capsule into space once it's in space. Next slide. So everything in the VAB, everything in the vehicle assembly building, is stacked on the mobile launcher, we like to call the ML, which is shown here in these couple pictures. The mobile launcher is 355 foot tall and weighs 10.5 million pounds. And once our team completes stacking of all the remaining Artemis 1 flight hardware in the vehicle assembly building, including the Orion spacecraft and the launch abort system, we will then roll out the rocket onto the launch pad for all the tests and system checkouts prior to launch. Now, speaking of rollout, the rollout is done on the crawler transporter, which is a piece of machinery that has been carrying rockets and spacecrafts to the launch pad for over 50 years, including all the Apollo missions, the shuttle missions, and now the Artemis missions. There are 2 crawler transporters at Kennedy Space Center, and each one is about the size of a baseball infield. They weigh 6.6 million pounds and can carry 18 million pounds, each of them. So empty, the crawler transporter moves, it blazes at about 3 miles per hour. But when we have a rocket on top of it, it moves about 1 mile per hour max, with many starts and stops to check a lot of different systems on its way from the vehicle assembly building to the launch pad, which can take at least an 8-hour shift. And then finally, it arrives at its final stop on Earth anyways, which is Launch Pad 39B. And there are several elements on Launch Pad 39B which make it great for launching SLS and other rockets. First of all, you see in the foreground kind of the water tower. The water tower holds roughly 400,000 gallons of water, and when released, flows at about 1.1 million gallons per minute during launch. And this is solely due to sound suppression in order to keep the acoustics down, because water is a very good substance for absorbing acoustics and sound. Without it, just the sound alone of the rocket and the boosters and the engines would probably shake the mobile launcher apart, maybe shake the vehicle apart, and maybe even parts of the pad. So the sound suppression system is absolutely critical in order to have a successful launch. In addition, you have the 3 lightning towers there that are shown, which protects the vehicle from dangerous lightning strikes in Florida, which we have very, very often, especially this time of year. Each lightning tower is 600 foot tall. And in fact, if you remember at the beginning of the presentation, one of the pictures was me on top of one of these towers, which is pretty breathtaking, not only a view, but it's pretty breathtaking getting there as well. On those 3 lightning towers, there's an elevator that goes on the outside of the tower to about the 450 foot level. Then you walk out on a catwalk, you climb a ladder for about 50 feet on the outside of the tower, while you're tied off, of course, but it's still on the outside of the tower for about 50 feet to get to about the 500 foot level. And then you see the we call them candlesticks because they look like candlestick looking things on top. Those are all fiberglass tubes that sit on top of the lightning towers. There's about 100-foot free climb in order to get to the top of them. So it's quite a journey to get to the top, but once you get to the top, the view is just almost nothing better. And then finally, we have the flame trench that's shown there in the middle. It can withstand a peak temperature of 2,200 degrees Fahrenheit, and it basically shoves all of the harmful exhaust fumes away from the vehicle during launch. Next slide. Next, we have the Launch Control Center, and really nothing could launch without the Launch Control Center. It's the hub of launch operations at the Kennedy Space Center. It's powered by some of the brightest minds in the world, and that team is responsible for overseeing all the processing and launch operations that we do at the Space Center. It's made up of software developers, coders, computer hardware experts, and they do the countdown and the launch sequence prior to launch. So they're the folks that if you hear on the TV or the radio, they're saying go, no go on things, ECS go, GCS go, hydrogen go. Those are the folks sitting right there in those chairs. Next slide. And then lastly is the Orion recovery operations. When NASA's Orion spacecraft returns to Earth following Artemis 1, it'll splash down in the Pacific Ocean off the coast of San Diego. And after splashdown, it'll be retrieved in the ocean by NASA with the help of the U.S. Navy, using what you see here in this picture is a open well-deck U.S. Navy ship. Now, this is a lot different than what we used to do during Apollo because, unlike Shuttle, where we didn't have to retrieve a capsule, during Apollo, they did something similar, but they actually used a crane on the side of a U.S. Navy ship, and it could get very tense at times because you can imagine it's like bobbing for capsules. So pulling using a winch and tow pin system, pulling it into the kind of the back of this ship, of this open well-depth ship, is much safer and more effective way to do it than we used to. Next slide. So as far as the missions themselves are concerned, Artemis is all about going to the moon and going beyond into deep space and onto Mars. But in order to get to Mars, we first have to go back to the moon, and that's where Artemis 1 comes in. So Artemis 1 will take the Orion spacecraft thousands of miles beyond the moon, farther than any spacecraft built for humans that has ever flown, over the course of about 3 weeks. And remember, there's going to be no astronauts in this one. It's basically just a test flight to make sure that we're ready to go on to the next steps. Next slide. Now, Artemis 2 will have crew. This will be the first time in over 50 years that astronauts will actually be in the moon's environment. Artemis 2 will have 4 astronauts on board. They will fly 4,600 miles beyond the moon, do a couple of slingshot maneuvers, and then come speeding back to Earth after that. Next slide. Then we have Artemis 3. And Artemis 3 is the big one because that's going to land the first woman and the next man on the moon. 2 of the 4 astronauts that will be going on this trip will go to the moon's south pole using a special vehicle that we call the Human Landing System and carry with them science tools and equipment and whatnot in order to do experiments. So they'll be living in the landing system for about 6.5 days. They'll collect samples, do some moonwalks, and then they'll return home from there. Next slide. Then, as I touched on earlier, Gateway, in addition to landing on the moon, in future Artemis missions, Gateway will basically act as an international space station, but orbiting the moon. So instead of being around Earth in low Earth orbit, it will be around low moon orbit. Again, that'll be in future Artemis missions and something certainly that we're all looking very much forward to. Next slide. And then finally, there's a lot more hardware that's going to be going on the moon that we're going to be developing, testing, and implementing. That includes the habitats, landers, new spacesuits, rovers, and so on, and all future Artemis missions, Artemis 4 and beyond. And again, really going to be looking forward to these missions here in the next decade or so. Next slide. So again, I really have the fortunate privilege to work on the shuttle program for several years, and then this program basically since its inception. A lot of work has been done to put together the largest, most powerful rocket in the world, and we are really well on our way here at Kennedy Space Center to do so. I really want to thank everybody so much for joining me today. I really hope you all enjoyed it, and I hope that you learned something about NASA's next, exciting steps beyond Earth. So thank you.
All right, let me unmute my mic. Thanks, Eric. I really appreciate it. And I'm going to go ahead and just jump into Q&A. I see that we have some questions already. But for those of you watching live on Facebook, please ask some questions of Eric and I. We'd love to tell you more about what we're working on here at NASA and at Jacobs. So our first question is from Aria, and she'd like to know, how do you launch the rocket? It's a pretty intense answer, I imagine, but maybe you can simplify it a little bit for us. I think you're muted, Eric.
Is that better? Can you hear me?
Yes, I can hear you now.
Right. Sorry about that. No, that's a very broad question. I'll try to give as specific answer as I possibly can. I mean, how we launch, we build the rockets. We build them in the vehicle assembly building, roll them out to the launch pad. How they actually launch is really through the fuel, and actually most of the fuel is liquid oxygen and liquid hydrogen, and that's what's actually used for the most part in order to propel the rocket, into low Earth orbit and then into space. From there, I was talking about the interim cryogenic propulsion stage. That is the piece of flight hardware that actually propels the Orion spacecraft beyond low Earth orbit, wherever they're going, whether it be the moon, Mars, or another destination. So hopefully that kind of answers the question, but
I think that's a great answer. Yeah. All right, so our next question comes from Robert, and this will be an interesting one. So are there any plans for Orion to fly on the Blue Origin or SpaceX rocket?
Not that I'm aware of anyways. Now, remember when I was talking about the launch vehicle stage adapter, like all those like kind of connection pieces? You can imagine that these sorts of things, especially like capsules, they're kind of they're slaves to the diameter of the vehicle. So the Orion space capsule has a certain diameter. SpaceX, their capsule, they have a certain diameter. Blue Origin, the same sort of way. So in order to potentially do that, they would have to come up with a lot of different adapters in order to be able to connect our spacecraft into theirs. Not saying that it's impossible, but I don't think that there's any plans to do that anytime soon.
Yeah, I haven't heard of anything either. All right, so our next question is, what is your day-to-day work life include?
Yeah, it's well, now that we're processing flight hardware, I'll say this. So during shuttle, it was a lot of fun. It was a lot of fun because there was always something going on. It was like a bee's nest around here. We were launching 3 orbiters. We'd have one in the VAB, one out at the launch pad getting ready to go, and then we'd have one in one of the orbiter processing facilities as well, coming back from launch. So there was always that bee's nest going on. And then, there was this transition period where we were doing a lot of design and development of all of the systems, both flight and ground, that it took in order to get this program, no pun intended, off the ground. So now that we're receiving flight hardware, and we're stacking flight hardware, and we're actually building the rocket, that feeling, that kind of like that bee's nest feeling is back. And so a lot of my day revolves around what's going on with the bee's nest. So, we always run into issues, we run into problems that need solved. And, I'm lucky enough to be in charge of a lot of really smart engineers that go and solve those problems. So at that million-foot level, that's my day-to-day. I solve the problems that are going on at the Space Center so that we can keep moving forward.
I bet that's a tough job. There is definitely a lot going on right now, for sure.
Yeah.
So you mentioned you have a lot of great engineers that are working with you right now. So yes. How do you become an engineer? That's the first part of the question. The second one, what's it like applying to be an astronaut? I'm curious about that process. Again, I've never applied, but there may be some folks out there that are interested in doing that in the future.
Yeah, sure. No, I can touch on that. I mean, I don't know if I'm the person to listen to because I haven't actually got an interview yet, but I did, I've had maybe step 1 of success for it. But for being an engineer anyways, when you're young, when I was a kid, I grew up on the shuttle program. I had like a little, actually, it was a pretty big toy space shuttle that I would, it was an orbiter that I would push across the floor and stuff. I always dreamed of like being an astronaut and working on the space program and stuff. But honestly, through my academic career, you know, I got my BS degree in civil engineering. I also was like fascinated by bridges, buildings, and so on. But still, you know, worked very hard and and had kind of a knack for math and science along the way as well. So it took a lot of work. I didn't really go into college or anything, or even in the grad school, knowing that hey, or even really having in the back of my mind, I'm going to go work at Kennedy Space Center. I really thought I was going to go work on bridges, to be honest with you. I was very fortunate after grad school that I applied to a job at the Kennedy Space Center, got an interview, and lo and behold, they hired me. And really, it's been history ever since. It's been a really fun ride. There's a lot of different ways to be an engineer. I think the way the engineer that I am, I've been very fortunate, and this has been a lot of fun. But I can't say you want to go and build bridges. If you want to go work on cars, if you want to go work on software and so on, there's a lot of different ways to have fun and be an engineer. And I chose one of those paths.
That's awesome. And you shouldn't be too hard on yourself. You made it farther than other people I know that's applied. You got a call back, and that's pretty awesome. Yeah. I know there's some astronauts that I think Clay Anderson tried like 10, 12 times. Really? Before he was finally selected. So yeah. Sounds like you're moving in the right direction.
Well, you put it that way, actually. It's funny you say that, because the time that I got called back was actually the first time I applied. Granted, the first time that I applied, there was if I'm remembering correctly, there was only like 5, 6, 7,000 applicants. This last time there was like 17,000 or 18,000 or something. It was just some ridiculous number compared to the first time that I applied anyways. So the pool was much smaller back then. I did get a call back then, but the last 2 times that I've applied, there's a lot of competition out there. I haven't heard anything about this last time that I applied, but I can still kind of fingers crossed, because I think they're still going through the process. And Patricia, I might have lost you there.
And hey there, Eric. I think Patricia's just on a little bit of a pause. Yeah, we had a little bit of a pause there for Patricia's sound. So we did have another question exactly about that question on astronauts for you. They asked, what kind of education do you think needs to be for someone to become an astronaut? So
education, so they it used to be that they only required a bachelor degree in engineering and one of the physical sciences. I believe also that included medical doctors, that included biologists, or if you ever seen the movie The Martian, he was a botanist and stuff. So I think all those types of degrees count as well. But this past time that they had their astronaut candidacy announcement, they did up the ante a little bit, and I believe that they required all of the applicants to have a master's degree as well. And it's probably rightfully so, just because of the breadth of the pool that is applying. And I don't know if they've had actually somebody that even hasn't had a master's actually go through the process successfully and get hired as an astronaut since the late 80s or even early 90s. So a vast majority of them even are PhDs. So having a master's is the minimum requirement now. Having a PhD is definitely helps your cause, if that's if that's the path that you want to take.
Well, we need a master's degree here at the library, so you're saying there's a chance.
Yeah. Sorry if you hear the announcement going over the, the speaker here.
Checking for any last questions here as we're coming up towards the end of our program here with everybody.
Sure. Yeah.
Yeah,
Fire
no,
away.
we have the same things going on here in libraries. Okay, I did have one last thing. Do you have a time frame? When is Artemis 1, 2, 3, 4? Do we have any kind of calendar yet for that?
So I'll give you the best answer that I know of at this point. So we're really we're working very, very hard in order to launch Artemis 1 by the end of this calendar year. But nevertheless, I was talking about earlier, we always have issues and problems that come up that we got to solve and make sure that we're doing the right thing in the right way. We're really working very hard for the end of this year, and that's going to be a really important milestone for us in the future. For Artemis 2, 3, 4, those are going to be in subsequent future years. Talking like 2023, 2024, 2025, around those timeframes there. So there's going to be a little bit of a lull in the action before we potentially get back to a little bit more of a steady cadence in the future.
And do you think that this is going to be as more recoverable than the shuttle was for turnaround for capsules?
So the capsule itself will probably have a pretty decent turnaround time. During the shuttle days, there was a lot of work that went into when the orbiter came back, making sure that it was ready for the next launch. When I say that there was like a bee's nest involved, it really was. There was a lot of work involved in doing that. And actually, it's interesting. At the beginning of the shuttle program, they actually thought that they were going to be launching those things, week after week within one another. And then, after, you get some unfortunate incidents like, Challenger and so on, you learn a lot, and you learn that, you really need to spend the time and make sure that you're doing it right. So I don't think that we're not going to get back to that tempo that we have during shuttle. We only have one vehicle with Orion. But and back then, we had at least at the end of the shuttle program, we had 3 orbiters that we were turning around. But it's going to be a similar type of effort. The Orion has a heat shield, just like the orbiter did on the bottom, and there's going to be cleanups for that. There's going to be cleanups for the capsule itself, checkouts, and so on. So it's not going to be exactly the same, but it'll be similar.
Okay. And we got one final question for you on,
sure.
I think I know the answer, but I want to hear from you. Who actually gets to name the rockets?
Oh, man. Well, NASA names the rockets. I wish I knew the answer to that. I don't actually know who gets to actually name the rockets themselves. That's a good question for even me. I'm sure Dr. Google would give a really good answer.
That's excellent. Well, thank you so much for being here, Sir Eric.
Absolutely. Yep. Really happy to be here. I'd really appreciate it.
We're going to it was really fun things. We have now all of a sudden everybody's getting any questions. We're going to wrap up and we're going to add these on. Don't forget this will be out and available for everyone out on the show. Thank you to there we go. Thank you to Eric. Thank you to NASA for all of the help today. If anybody has any questions, creationstation@broward.org. We'll see you all soon. Thank you very much.